What was that? Well, that was my rebound hardness tester doing a test on this piece of high-speed steel, and it showed us on here equivalent of a Rockwell C of 65, which is about what we would expect for something like that. Let's try again with this other piece of high-speed tool steel. And we get 62. It's a little bit less than the other one, but they all vary somewhat. Now let's try a piece of 6061 aluminium, heat treated to T6. Reset. And 27 showing on here for the Rockwell. Later on in the video we'll look more closely at what these numbers mean. Well, we've seen this device working, so let's now have a look at the theory behind it and how easy it is to make it. So we'll start off with a quick review of different hardness testing methods. Basically they come into two categories. The more traditional one is an indentation device, and the other type is known as a rebound type, and this is the category that this device comes into. With the indentation type, basically you have some sort of very hard stylus, diamond, something like that, of an appropriate shape depending on the type of tester that you're using. The main ones are Rockwell, which is American, Brunel, which I think was British, and Vickers, I think also that was British. They use different types of indenter. The Rockwell uses a pointy shape, the Brunel uses a ball, the Vickers uses some sort of diamond shape, I believe. Yeah, these two are the main ones, and basically they have a machine which can apply a known load onto the indenter, and then they measure the amount of indentation in the material. So they actually leave a permanent mark in the material where it was being tested. Usually a fairly small mark, but a mark nonetheless. These machines are generally bench mounted, relatively small machines, so you can only have a relatively small workpiece. You actually have to take the workpiece to the machine. Now, looking at the rebound ones, Mr. Shaw patented what he called a celeroscope back in 1910. Essentially what that does is it drops a ball under gravity and it measures the rebound height. The problem I had when I was trying to use this very simple one was actually determining with any repeatable accuracy how high the ball bounced. And I considered trying to add some electronics to this to measure how far it was coming up, but that's not as simple as it might sound. It's relatively easy to have some sort of sensor here, say, and detect whether the ball bounces back past that or not, but to actually measure where the ball comes to is a little more difficult. So I started thinking that maybe if I measured the velocities, now that would be easier. So I thought if I measured the drop velocity and then the rebound velocity, the ratio between the two would give me some indication of the hardness. And then I found out about the lead machines, which were patented in 1976. Now they work on exactly that principle. They measure the velocity ratio from when the ball hits the workpiece to what it is when it bounces back. Now they're a fairly compact machine, unlike the Shaw, which used gravity to bring the ball down. The Lieb has a more complicated impactor. It has a magnet in it as well as the hammer which hits the work, and the magnet passes through a couple of coils which work like an LVT, a linear velocity transducer. They're a fairly compact and portable device because instead of forcing the impactor in by gravity, it uses a spring. Well, for my purposes, I was quite happy to use gravity. Let's look in a little bit more detail as to how I made mine. Well, basically we've seen that I've got a tube. It's a steel tube. It's 1/2 meter long, so the drop distance is 1/2 meter. With the shore system, because you measured the rebound height, it was the height from which you dropped the ball was important because that would affect it. By measuring the velocity ratio, as the lead did and I proposed, the drop height is not so important. It affects the impact energy of the impactor, but it doesn't affect that ratio of velocities. Because if you drop this from half height, it will impact a bit slower, the rebound will be a bit slower, but the ratio will be very much the same. So the hardness we measure will be very much the same. The 1/2 meter for me was convenient for several reasons. One is I had a piece of steel tube that was 1/2 meter long. That's a pretty good reason. The other one was dropping it from 1/2 meter had the same velocity on impact as the lead. This meant that because although I was using a ball dropped by gravity and the lead system was using a more complex impactor powered by a spring, the velocity of our impactors at the surface of the material we're measuring was in the same region. So I thought that might relate a little bit better to an existing scale. So I've got that 1/2 meter tube. This aluminium piece on the bottom is here for two reasons. One is it gives me something to hold on to hold it firmly against the workpiece that I'm testing. It gives me a support for 2 infrared diodes and 2 infrared transistors, which are used to measure the velocity 7 millimeters above the contact position, because that will then allow the ball to sit down without interfering with the sensing. Now the internal diameter of this tube is 8 millimeters, and I've got 2 sizes of ball. The larger one up here is 7 millimeters, and the smaller one down here is 1/4 of an inch, which is 6.35 millimeters. So they're both quite loose in the tube, and they give absolutely identical readings. It doesn't matter which one I use. There's one thing to be concerned with is that if you had a ball that was a reasonably tight fit in the tube, as it falls, it's got to push air ahead of it or past it up through here. Now on the bottom, machine 2 grooves. These are to let air out as the ball's coming down, but also by using a 7 millimeter or 6.3 millimeter ball in the 8 millimeter tube, there's some air clearance past it, so as the ball's coming down, it's not slowed up very much by air resistance. So let's have a quick look at the inside. We've got our tube here, which sits on the work, which sits on something solid. We drop a ball down from here, it reaches the bottom and bounces back. When it reaches here, due to gravitational acceleration, it'll have a certain incident velocity, which we'll call VI for incident velocity, and then it will rebound with a velocity dependent on the hardness of this material, and I'll call that VR for rebound velocity. So we can then determine the ratio of VR over VI. Now the Lieb hardness scale is simply that ratio multiplied by 1,000. They did that, Mr. Lieb said that's a new hardness scale. But they have related that quite closely to the other hardness scales, the Rockwell scale, the Brunel, etc. So if my device worked anything like the Lieb one, I could use this and relate the hardness to those other scales, which would be extremely useful. It wouldn't be too difficult to make a machine that worked very much like the Rockwell hardness tester or the Brunel one. With the Rockwell machine, it's a matter of applying a certain load, and the loads are defined depending on the actual Rockwell scales you're using, and the depth of indentation is measured. That's measured with some form of dial gauge. Brunel system, on the other hand, uses a much heavier force. It forces a ball into the material, but it doesn't measure the indentation depth. You then have to use a microscope or something similar to measure the diameter of the indentation that's left. Now you can imagine that that's a lot slower and less precise than the Rockwell idea of actually measuring the penetration. I considered making a machine like the Rockwell, but I wanted to measure the hardness of things like this motorcycle cylinder head, and larger objects as well. So a machine that only took relatively small work pieces wasn't of all that much use to me. I needed something that I could bring to the workpiece, and that was what the Lieb type system offered. Because the Lieb system was spring loaded, it doesn't have to be held vertically to use gravity to drop the impactor. But I was quite content to use gravity. There'd be all sorts of difficulties of doing a really good job with a spring, yet gravity doesn't change very much from day to day. Let's look at how I actually measure the velocity. This is our tube. Ball has dropped to the bottom. Just above that, I have opposite holes drilled and then enlarged. In one I fit an infrared LED, and in the other one, in the enlarged part of it, I fit an infrared transistor. So this one passes light across. If there's no ball in the way, the light comes through and the transistor picks it up. When a ball is in this region, it blocks off that infrared light, and the infrared transistor detects that, and that's passed on to the processing electronics. But I can't just measure the velocities with one, so I put in a second one up here in the same way. Now, if I'd actually stacked them as I've drawn it here on a two-dimensional plane, I wouldn't have been able to get these close enough together. So what I've done, one lot goes this way and the other lot goes that way. So then they can come as close together as necessary. So I've got approximately 5 millimeters between these, and this is up greater than 7 millimeters, so that when the ball's at the bottom, it's clear from here. The ball comes down. First of all, it blocks off the light from the first one, so that's the signal that something's happening, and that is the start of measuring the drop velocity. And then it comes past the second one and it blocks that off. So that's the signal that it's gone by. I know the distance between the top and bottom ones. The electronics measure the time, and hence we calculate the velocity. That's the incident velocity. And then it hits here, it bounces back, so the bottom one gets shut off first. That's the start of the timing interval. Then the upper one gets shut off, and that's the end of the timing interval, and we can calculate the rebound velocity. And then it's just trivial to calculate our velocity ratio, and hence get a number like the Lieb hardness number. Well, I did that. My very first test was without any calibration, purely getting that lead number because of the velocity ratio. My first test was on this piece of high-speed tool steel, and after converting the number that I got to Rockwell C according to the Lieb conversion tables, I got a value of 64 Rockwell C for this piece of high-speed tool steel, which is right in the range that you would expect for such material. I then tested other materials and got equally close results to the hardnesses that one would expect for that particular material. I was a happy boy. Well, since I did the first sequence with this simple little drop tube, I thought it might be interesting if we could look at it in slow motion, because as I mentioned, the biggest difficulty I found with this was determining at real speed just the maximum height that the ball bounced to. So I thought, well, if I do the video at a higher frame rate and then play it back slower, we might be able to have a useful tool from this and get a fairly accurate and repeatable measurement of the apogee. This is on a piece of 4140 steel. One thing to notice there is there's not very many repeat bounces on that material. So now we'll look at it in slow motion. Now we've put it on the high-speed steel again. Quite a lot of repeat bounces. Well, before we finish up, we need to talk a little bit about hardness scales and the dangers of how we use the numbers. First of all, just looking at the Rockwell, the huge range of scales for different materials and different special purposes. For our purposes, normally with metals in the workshop, there's probably the B scale and C scale, which are the most used. The B scale is for aluminium, brass and softer steels, etc. And the C scale is for harder steels. Steels that are harder than 100 on the B scale. The actual numbers of the C scale range from about 20 up to 64, 68. With the Lieb, its use is aimed very much like the Rockwell C, in that it's the harder steels, and its range in terms of the numbers it produces is from around about 500 to 870, which converts more or less to the 20 to high 60s. In the C scale, we may well measure things with this, with a rebound tester, like the one I've built here, outside of these ranges. Well, basically all that means is the numbers that we get wouldn't be accepted anywhere that was adhering to the actual hardness standards as set down by various institutions. But it can still give us some useful numbers for most of our purposes. For example, just done a test on some 4140 steel, which would be quite a legitimate steel to fit into the Rockwell C scale and the Lieb scales. And we've got a hardness on the Lieb scale, which is just the velocity ratio scale, of 707, and when converted to the Rockwell C scale, we've got a value of 48. Because this is a fairly hard steel, it would fit into the standards and the ranges of these two hardness standards. Now let's repeat that test on some 6061 aluminium. We've now got a value on our Lieb scale of 556 and on the Rockwell C scale 27. Now both of those numbers fit within these ranges of hardness, but it doesn't comply with hardness standards because we're measuring aluminium on scales that are meant for steel. For our purposes it doesn't matter. I could put another block of aluminium here that was softer and it would tell me that it was softer. it's still quite a useful tool, even though we need to consider the scope in which we're using it compared to the scope of the standards. Okay, well I think that just about wraps up the theory, the way I built the mechanical parts of mine. In a second part we'll look at how I built the electronics and the programming for the Magic Box. If you like this video or any of the others, please share, subscribe to my channel, and don't forget to click the button to receive updates of any other videos. Thanks for watching.